Water Resources, Chapter 13. This is a case history Long Island, the groundwater pollution, a serious problem on the western end of Island since the beginning of 20th century. Groundwater below Nassau County is tremendous, yet intensive pumping causing as much as 15-meter decline in water level. So salt water intrusion due to declination in water level. So urbanization triggered more serious water pollution, urban runoff, sewage and fertilizers, road salt, industrial and other waste and landfills. So most of them have been closed. So this case history you can read from the book, and this is the place where you can see the picture of Long Island in Nassau County, and mixing of this salt and freshwater interface. So right here you can see the fresh groundwater and the salty groundwater. So this is where the problem comes in. So when we talk about water resources, we talk about water pollution, and that's another chapter that we are going to cover in this class. But this is just the beginning and the very first time that we are going to talk about the water resources. So we need to make sure that we understand what is water and what is the process that we are getting water, and what are the different processes or the components that water involve. So the cyclic nature, similar to other elements on the earth crust, like you may heard about the carbon cycle, you may heard about sulfur cycle, nitrogen cycle. Likewise, the water has its own cycle. It's a cyclic nature, the water cycle, or it's known as hydrologic cycle. This is, in definition, is global movement of water between different water storage compartments. So when we think about compartments, maybe clouds, maybe lakes, maybe oceans, maybe atmosphere. So likewise, in different water storage in different compartments. So this is the global movement of water between these different compartments. When it comes to global distribution of water, the abundance not a problem. The distribution in space and over time a problem. So we have polar regions, polar caps, enough large amounts of water, but the distribution in space is the problem. It's not distributed similarly equally in the places that we really need water. So supply versus use a problem for sure. So we have limited supply in some places, but it's heavily used. So this is where the problem comes. This is where the water is a resource and it's non-renewable, and we need to protect it. More than 99% of Earth's water is unavailable or unsuitable for beneficial human use, either salt or ice. All people compete for less than 1% of Earth's water supply. So you can imagine water is already a resource. So that is precipitation. Water's horizontal movement, either surface runoff like rivers or streams, and shallow subsurface through flow, and the groundwater flow. So this is where you talked about the horizontal movement. If you think about the groundwater flow patterns, that's a horizontal movement until you reach to the water table. The water from the place where they get infiltrated from the surface water, they get into the pore spaces in between soil particles, and they're percolating through and coming to the groundwater table, and then from groundwater it's moving every different direction horizontally. So that's the horizontal movement of water. So the world's water supply. So here is the chart that you can refer to when we need to talk about the water volume, surface area, location, and percentage of total water, and estimated average resident time. So what is resident time? You know, from your first or second chapter you talked about what is resident time. That means how many years or how long this water is going to survive in that particular place, in simple explanation. So oceans, thousands of years. Atmosphere is 9 days, so that's resident time is much shorter. And lakes, It's like 10 years, and ice caps or glaciers up to tens of thousands of years and longer. So that's why we always have the ice in the water in the ice caps. So you can clearly think about this, and that's easy to understand what is the resident time means. And when it comes to the surface area, so oceans cover a large surface area, and also groundwater. If you would never think about it, but the groundwater covers a large area as well. The water volume, the highest water volume obviously in oceans, and then the ice caps and glaciers when it comes to the groundwater. Okay, so the percentage of total water is mainly the oceans have the highest percentage of total water. Surface water, that's also known as surface runoff, has important effects on both the transportation and erosion. So surface runoff is responsible to transport the sediments at the same time eroding the sediments. They're taking sediment particles from one place to another. So that's called the erosion. And also drainage network is something that we need to talk about. So the surface runoff, there are different types of drainage patterns that you talk about. We talked about drainage basin and different patterns like rectangular, trellis, or radial. There are different drainage patterns, drainage network that you're talking about. So that's all contributes towards the surface runoff. Drainage basin or watershed, it's an area of land that contributes water to a particular stream or river, a basic unit of landscape. So that's a drainage basin or the watershed. So that's where rivers starting from. And basically these are mountainous regions where you can have the springs and they start forming the water, and then they run off, like they're moving away from that watershed area. Drainage divide, that is a boundary or imaginary line between drainage basins. So two drainage basins are demarcated, or these separated by this divide. So divide is important. That's an imaginary line between two drainage basins. Stream order and size of the drainage basin. So this is something we are not going to talk in much details. However, that's also important. It's in the order 1 drainage or 2 or 3 likewise, and the size of the drainage basin is also important to get an idea about how much water that exists in that particular drainage basin. Factors affecting runoff and sediment yield: geological factors, topographic factors, climatic factors, vegetation factors, and of course the land use practice factors. So geological factors, the type and structure of soil and rocks, that's also important, and that determines the runoff and the sediment yield. When you think about the permeability of soils versus impermeable layers of soils, so that kind of changes the surface runoff. And also topographic factors, the high relief versus low relief, steep angle or gentle slope angle, so that also contributes towards the runoff. And climatic factors, the type, intensity, duration, and distribution of precipitation, that's also important when it comes to the surface runoff. Vegetation factors, the type, size, and the distribution of vegetation is also important when it comes to the surface runoff. Groundwater. Oh, when it comes to the groundwater profile, I'll show you a picture later, the next slide. But there are a couple of words that you should understand, and you should be able to define what it is. Vadis zone, also known as zone of aeration. So that's the unsaturated zone, and you can have the water vapor in here, but mostly you have air within the soil particles. Zone of saturation is where you have the soil particles completely saturated with the water molecules. The water table is the boundary between the zone of aeration and zone of saturation. Perched water table, that is the local water table above a regional water table. So that is more temporary water table, I should say. When it more rainfall, then you have perched water table. When there's a drought, so it's going to disappear, so something like that. And here is the picture to show you zone of aeration or the Vedos zone versus zone of saturation and the water table. So the flow of groundwater, like we mentioned before, is horizontal. Aquifer. These words are also important and you should know the definitions and examples for each different terms. So aquifer, a unit capable of supplying water at an economically useful rate. So in this case, the aquifer could be water-rich aquifer or sometimes it could be oil-rich aquifer. So that unit is capable of supplying water at an economically useful rate. Aquitard or aquiclude is a confining layer or unit restricting and retarding groundwater flow. So for example, if you're thinking about the clay layer, so that's impermeable layer and that considered as the aquitard or aquiclude. Aquifer, for example, sandstones are good aquifers because they are highly porous and highly permeable. So they consider as the aquifers where you can store oil or water within the soil particles. Unconfined aquifer, that is no overlying confining layer. The confining aquifer is with an overlying aquitard layer. So we'll look at some examples later. So perched aquifer, like I mentioned, that's a local zone of saturation above the regional water table. Here you can see the Vedos zone and the zone of saturation and the water table. And if you look at these two different areas, so it's sandy soil not saturated and this is sandy soil saturated. You can see the blue shade to this picture, so that's giving you an idea about water enriched area versus no water area, or very less just the water vapor in here. And the groundwater recharge and discharge. So the recharge zone, area where water infiltrates downward from surface to groundwater. That is where you're going to recharge the groundwater table. Discharge zone, that's the area where groundwater is removed from an aquifer such as spring, well, or river. Influent stream is about the water table. Recharge water to groundwater may be intermittent. Effluent stream, that is the perennial stream with the addition of groundwater when precipitation is low. So these are some terms that you need to understand. If you have any question about these, let me know. Groundwater pressure surface, so generally declining from source along the flow from recharge area to discharge area. Artesian well, the water self-rising above the land surface in a confined aquifer. So cone of depression is drawdown cone of groundwater in a well. Hydraulic gradient, the gradient of water table generally following the topographic gradient. So for example, if you have a hill and the high elevation to low elevation, so the gradient is, you're going to see the water table is changing from high elevation to low elevation. The elevation of water table is also changing according to the topography. So the gradient is always, you consider like high versus low. So it's usually higher water table and it's going to flow towards a lower topographical lower area, and the water table follows the same pattern. Hydraulic conductivity is the ability of rock materials to allow water to move through cubic meters per day per square meter. So hydraulic conductivity is very important concept in hydrogeology especially. So we'll be talking about that later in depth, but not for this class. So this is just more introductory level environmental geology class. When you talk about this groundwater movement, we should talk about what is hydraulic conductivity, but we are not going to calculate, or we are not going to talk about any Darcy's laws, but they all come after the hydraulic conductivity concept. So that's the ability of rock materials to allow water to move through. So if you think about sandstone, that's the hydraulic conductivity is higher compared to clay stone. Porosity, the percentage of void spaces in sediment or rock to store water or oil. So that's porosity. Permeability is the measuring the interconnection of pores in a rock material. So that's permeability. So porosity and hydraulic conductivity. If you have higher porosity, and you should expect to see higher hydraulic conductivity. So for example, the sand, the porosity is high, but at the same time, it depends on the size of the material too. For example, the clay has high porosity, like 50%, very, very tiny particles, but the conductivity is really low because there's no pore spaces. Even though they're pore spaces, they're not interconnected. So they need to be interconnected in order to transmit the water, in order to conduct the water. So that's the idea. But sand, it's you have porosity 35%, but having these pores connected each other, so hydraulic conductivity increases. And in granite, porosity is 1% and the conductivity is very, very low. Sandstone hydraulic conductivity is 28.7 meters per day, that is higher, and because you have pore spaces in there. But the gravel, look at the gravel, so it's 25% porous. The hydraulic conductivity is very high because you have these pore spaces. The 25% of porosity is interconnected. So this interconnection of these pore spaces is important when you talk about hydraulic conductivity. Available groundwater estimated about the total flow of the Mississippi during last 200 years. The groundwater as primary drinking water source for nearly 50% of US population. Groundwater overdraft problems like extraction rate exceeding recharging rate, like no precipitation but more extraction in many parts of the country, and particularly some states in Great Plains regions. Estimated 5% of groundwater depleted, but water level declined more than 15 meter in some areas. So the groundwater is the basic water supply for most of the places that you go within the US or in other countries. But the recharge and the discharge rate needs to be matched up. So if you have more and more discharge, more and more extraction of the groundwater, but no recharge or less recharge, that can cause the problem. And that's one of the problems, as you can see in this picture. So that's called the cone of depression. So we get depressed when we don't have things, but the same way, so the water table, it's get depressed. So this is called the cone of depression, and that because of the over discharge from the water well, and the groundwater trying to form this kind of like all these groundwater flows towards this well, and that's kind of creating the cone of depression. So that's a feature that you can observe if you have higher discharge and no or less recharge. Overdraft of groundwater leads to a lower water levels of streams, lakes, reservoirs, etc. Overuse of surface water that yields lower discharge rates of groundwater. Effluent stream in groundwater discharge zone tends to be perennial, and influent stream in groundwater recharge zone above the water table often intermittent or ephemeral. Special linkage area like sinkholes and cavern systems in the karst terrain. So the karst topography, what does that means? So those are carbonate environments. So the karst topography where you talk about limestone caves, for example. So that's where you're going to have sinkholes. That's these limestones, these are carbonates, so they react with the liquids, especially the acidic or slightly acidic liquids, and they're forming these holes. And with that, like you should think about like the sinkholes, and these areas are not good for building up any structures. However, for the groundwater, so these can be good places that they can transmit water to one place to other easily because of these less strength in the rocks, especially the carbonates. So interactions between surface water and groundwater. So here is a picture showing you that the springs and the lakes, the groundwater is kind of recharging the lakes or these wells, and then wherever you have cut the groundwater table, and that's where you're going to see this water exposed in the in different places as a river or as a lake or as a well. Uh, so karst topography problems. So the water pollution occurs where sinkholes have been used for waste disposal. So people used to use the sinkholes as the waste disposal sites, which is not good because the carbonate is not a very strong or very strength rock. So that's a very weak rock and that can do a lot of leakages because they get dissolved, as I mentioned, slightly acidic conditions they can dissolve because these are carbonates, so that can cause leakages if you dispose the waste that's not protected. So carbon systems are prone to collapse, producing sinkholes that may form in areas that damage buildings on the ground surface, roads, and other facilities. In many areas underlain by limestone, such as the Edwards Plateau in Texas, groundwater is being mined. As a result of the mining, important karst springs, where water emerges from caverns, are being changed, causing a reduction in biodiversity. So that's a big environmental issue. And water use. So off-stream use is a removal or diversion from its surface water or groundwater sources temporarily. So example, we use it for irrigation, thermoelectric, or industrial use. The consumptive use is type of off-stream use of water without intermediate return to the surface water or groundwater, such as transpiration and human use. And in-stream use is navigation, fish, and wildlife and recreational uses. So these are different types of water uses. In major urban areas, so over withdrawal of groundwater can be an issue. So that's over discharging water. Overuse of local surface water can be an issue. So threats of local urban landfill to the water supply. For example, Long Island, New York. That's a problem. So water import uses and problems. So what is distance to transport? How much water available? From where? So conflicts with other areas, litigations, and long range planning. So these things come into play when it when we talk about the water management actually. So trends in water use. So based on the data from 1950 to 1995, surface water use far greater than groundwater use. The rate of water use decreased and leveled off since 1980. Irrigation and thermoelectric are major fresh consumptive water use. Less fresh water use since 1980 due to new tech and water recycling. So here is the chart that you can see the population increasing and the groundwater versus surface water versus total water. And you can see from 1950 to 2005 population increases and the water usage increases, and especially the using the groundwater is kind of decreases, but using the surface water increases, but the total usage of water increases. The withdrawals in billions of gallons per day. So that number is increasing. So here is another chart. The withdrawals in billions of gallons per day in y-axis and x-axis the year. So 1950 to 2005. So total withdrawals is kind of equal out after 1980 to 2005. So because people use other systems, other supply of water rather than this groundwater. So water conservation. Improved agricultural irrigation could reduce water withdrawals by between 20% and 30%. Engineering technology and structure, regulating irrigation and reducing evaporation. So better technologies in power plants and other industries, so less use of water due to improved efficiency. So domestic use of water, like urban and rural, accounts for only 10% of the total national withdrawals, can be reduced at a relatively small cost with more efficient bathroom and sink fixtures. You can imagine how much water that we waste when we go to bathroom or at the sink. Global water conservation is a virtual water budget. conservation of water at the global scale. So this is import and export plan. So you can see some countries, they have enough water, they can import, I'm sorry, they can export, and then the other countries who needs water, they can import the water. So this has become global scale conservation plan. Water management. So needs for water management, increasing demand for water use and water supply problems in semi-arid and arid regions, water supply problems in mega cities of humid regions, and water traded as commodity, capital market and regulations. So these things needs to be discussed when it comes to water management. And aspects to be considered is the natural environmental factors, geologic, geographic and climatic, human environmental factors like economic factors, social and political, and some of the strategies would be more surface water use in wet years and more groundwater use in dry years, and also reuse and recycle water regular basis, as well as emergencies like fires. Managing the rivers, so dam construction could save water and use in useful projects like hydropower projects, and impact on flood frequency and impact on sediment distribution, particularly downstream, and impact on wildlife habitats, and control the planned floods. So when it comes to the river management, these are the things that we need to pay attention. And also the water and ecosystems. Changes in response to climate, nutrient inputs, soils, and hydrology. And general tendency is to increase human use of water, increase degradation of natural ecosystems. So overall reconciliation between multiple water uses. So water resources, development, that's dam, reservoirs, canals, and associated impact on surface water environment. Reconciling the uses of water in agriculture, industry, urbanization, and recreation, and the protection of wetland and water resources. That's also important facts. The wetlands like swamps or marshes, bogs, prairie, potholes, vernal pools, and the wetlands are one of the nature's natural filters. So the plants in wetlands may effectively trap sediments, nutrients, and pollutants. Freshwater wetlands are a natural sponge. During floods, they store water, helping to reduce downstream flooding and release water after the flood, nourishing low flows of river systems. And wetlands are highly productive lands where many nutrients and chemicals are naturally cycled while providing habitat for a wide variety of plants and animals. Freshwater wetlands are often areas of groundwater recharge to aquifers. Some of them a spring fed marsh, for example, are points of groundwater discharge. So, emerging global water shortage. Isolated shortage of water, that's indication of a global pattern of water shortage. So, depleted water resources, overdrafted aquifers, dried lakes like Aral Sea, and troubled streams like Colorado and Yellow River not reaching seas some years, and polluted limited water resources due to development and increased waste. And the demands for water resources tripled as populated more doubled last 50 years and growing fast next 50 years. And the global warming that's causing more problems. So these are some of the critical thinking points as your take home message from this chapter, and with that we're gonna conclude the chapter 13. If you have any questions, please feel free to email me or put in the discussion board.